Hey guys, Alexander here, and in this video I will be covering all of the discrete distributions that we discussed in the probability theory playlist, but in R. So let's start off. This R script, is intended for you to get familiar with the discrete distributions that we've covered in R. It will also allow you to comfortably confront various assignment questions that you are likely to face in your studies. So the distributions that I will be covering are the Bernoulli, the binomial, the geometric, negative binomial, and Poisson distributions. I will be covering how to get the probability mass function, the cumulative distribution functions, and the moment generating functions of these distributions. So firstly, there are a few packages that you need to load and install if you don't have them already installed. So just uncomment these lines and then install all of these packages. And so it's the DevTool library, which will allow you to install my moment generating function package. The stats library, that should by default be in RStudio, but the stats library will give us the access to the probability mass function and the cumulative distribution function. And the MGF library, the MGF package, which will allow us to get the moment generating functions as well as calculate the moments of these 5 distributions. So firstly, let's start off with the Bernoulli distribution. Just a reminder, the Bernoulli distribution models the outcome of a random experiment that can either be a success or a failure. In this case, we let the random variable x be a Bernoulli distributed random variable with a success probability of a half, 0.5. So the easiest way to access the Bernoulli distribution's probability mass function in R is to use the binomial distribution probability mass function, but we simply set the size equal to 1 because a binomially distributed random variable with one trial is the same as a Bernoulli distributed random variable with the same success probability. So let's say if you were asked what's the probability for a fair flip of a coin for the outcome will be a success. Well, we let heads represent a success, then we use the D binom. So D binom with size equals 1 is the probability that the outcome of the coin flip will be a success. The probability for that is a half. Because we have half a chance, it's a fair coin, half will be the probability that we observe a head. What's the moment generating function for a Bernoulli distributed random variable? Well, we use the MGF function from the moment generating function package. And we see that it is 1 minus p plus p times e to the t. This is exponent, the number e. So it's e to the t. Now let's move on to the binomial distribution. For this example, assume that the random variable x follows the binomial distribution with the number of trials being 10 and the success probability being a half. So binomial example probability mass function. What's the probability for a fair coin that we will observe 5 heads in 10 tosses? So that is, we use the D binom. So you will see in R, it's usually D to give the distribution or the density function of the random variable. So D binom will give us the probability mass function for the binomial distribution. We set the size, which is the number of trials, to 10. The success probability is 0.5, and the value that we're interested in for the number of heads or successes is 5. So let's submit this line of code, and we see that the result is 0.2461 roughly. That's the probability that the random variable x would take on a value of 5. Now let's look at the cumulative distribution function. What is the probability of observing less than or equal to 5 heads in 10 tosses? So we use p binom, which returns a probability that that random variable x is less than or equal to q. So the probability is 0.6230469. So this p binom function has a bunch of arguments in it. We can type it like this. We have lower tail, which gives us the probability that x is less than or equal to x. If you set this lower tail argument to be false, then it will give you the probability that the random variable x is greater than x. So less than or equal to x, the default value of this p binom will give us the cumulative distribution function. Its default value, lower dot tail, equals false. Equals true, sorry. As you can see here, this result for the lower tail equals true is the same as leaving it out. So we end up with the same results in both cases. Next, I will show you how we would address a question where we wanted the upper tail probability, the probability that the random variable x is greater than some realized value. So what is the probability of observing more than 5 heads in 10 tosses of the coin? Well, we can use the lower tail, so we say 1 minus the probability that x is less than or equal to x, so 1 minus the CDF, which gives us this answer. Or we can set the argument lower.tail equal to false. Then we get the upper tail probability, which is the same as 1 minus the lower tail probability. So that's how we can use this lower.tail argument and change it from true to false to get upper tail probabilities. Lastly, I'll show you how we can use the MGF package to get the moment generating function. You just need to specify the distribution is binomial, then it will give you the moment generating function of the binomial distribution, which is 1 minus p plus p e to the t to the power of n, which we see is the same as the moment generating function for the Bernoulli distributed random variable, but to the power of n. To the power of n. And if n is 1, then we see that the binomial in fact becomes the same as the moment generating function for the Bernoulli. Over here, the moment generating function package also has a function called MGF evaluator. This function is very helpful to evaluate the moments of a specific distribution. So let's find the second moment and the second centralized moment for the binomial distribution, with number of trials being 10 and the success probability being 1/2. Note that the second moment is the expected value of x squared. The second centralized moment is the same as the variance of x. So we run this code and we get all these various lines of output. This is what the formula would be for the second moment of the binomial distribution if we derive it from the derivatives of the moment generating function. This is before the value of t has been evaluated at t equals 0. So if you were to plug in t equals 0 here by yourself, you could find the formula for the second moment in terms of p and n. And you would find that second value of the moment was 27.5. The formula for the second centralized moment is all of this. And if you were to plug in t equals 0, you would find that this should simplify to n times p times 1 minus p, npq, if you remember from the introduction to the binomial distribution video. The second centralized moment's value is 2.5. That is the same as the variance, which is n times p times q. As n was specified to be 10 in this case, 10 over here, and p is 0.5, so it's 10 times 0.5 squared, which is 10 times 0.25, which is equal to 2.5. So that's how we evaluate the moments of the binomial distribution using the moment generating function, evaluator function. So let's get to the geometric distribution. And there's a very important thing that you need to note here. There are two different formulations of the geometric distribution and thus also the negative binomial distribution. One formulation counts the number of trials until your first or your rth successes occur. Another one counts the number of failures. So the one that R uses by default is the number of failures until your first success. So if you want to convert from the number of, if you want to convert the one that you might be used to, which is the number of trials until your first success, to the number of failures, you just need to say the number of failures until the first success is equal to the number of trials minus 1. And I'll show you why that is the case over here. So let's take a look at this example over here. What is the probability that the number of failures is 1 until we reach the first success? Note that this is the same as the probability for the number of trials until the first success to be 2. So we need 2 trials. The first trial is going to be a failure. The second trial will be the success, so then we will reach our success. So if we were interested in using base R, the stats function package to calculate this probability, as you might be used to it, it would give us this answer, 0.25. we need to change x from 2 to 1 because we have to subtract. We have to subtract 1 to convert it to the number of trials until the first success, because we're always going to have 1 success as being the last trial. Next thing that we need to do is the probability that the number of trials until the first success is equal to 1. So number of trials until the first success equals to 1 is the same as saying we didn't have any failures, because our first success was on our first try. So that means the number of failures x is 0. We didn't have any failures. And if we run this line of code, we get the answer of 0.5. Next is the cumulative distribution function. What is the probability that the number of failures to the first success is less than or equal to 1? Well, we can go and get the summation of these two probabilities, but that's a bit tedious. So there is a function pgeom which returns the probability that the random variable x, which follows a geometric distribution with success probability of a half, is less than or equal to q, which is 1. So the probability that x is less than or equal to 1. So that is for the number of failures. So if the number of failures has to be less than or equal to 1, that means the number of trials till the first success was less than or equal to 2 in the different formulation. And if we run this line of code, we find it is 0.25 plus 0.5. So it's the probability that x is 0 plus the probability that x is 1, which is equal to 0.75. Next, let's look at the upper tail of the probabilities. So we can always just use the 1 minus the probability that x is less than or equal to x, which is 0.25, and we see that 0.75 and 0.25 sum to 1 because these two events are complements to each other. Or we can just use the argument lower dot tail and set it equal to false. Then we'll get the probability that the random variable x is greater than 2, which is 0.25. Lastly, if we want to find the moment generating function, and we don't want to go and refer to Wikipedia or so, the function is built in the ngf package. You just call ngf with geometric, and it would return to you the moment generating function for the geometric distribution, which is pe to the t, all of this divided by 1 minus p times e to the t. So next we will be looking at the negative binomial distribution. If we let the random variable x follow the negative binomial distribution, with the number of successes being 3 and the success probability being a half, then if we're interested in what is the probability that the number of trials till the rth success is a 3 trials, so we have to have 3 trials until we reach our third success. That means 3 successes in 3 trials means we have no failures. And since in R, the random variable x, which follows the negative binomial distribution, is considered as the number of failures, then we need to always ensure that our x is specified correctly. X is the number of failures. So 3 trials to reach 3 successes means we had no failures. So we have to go and submit this command, dn binom, with x equals 0, the size equal to 3, where size is the number of successes, and the probability being our success probability of a half. If we submit this line of code, we find the answer to be 0.125. In the next example, let's consider 4 trials until we reached our third success. That means that the number of failures was equal to 1. So x equals to 1. The probability for that event to occur, the probability that the random variable x is equal to 1, is equal to 0.1875. So if we're considering the negative binomial distribution's cumulative distribution function, then let's ask ourselves, what is the probability that the number of trials until the rth success is less than or equal to 4? This is the same as asking what's the probability that the number of failures is less than or equal to 1, because we have number of trials minus the number of successes, which gives us the number of failures, because at any one trial can only be a success or a failure. The probability for that event is given by this line of code. Pn binom with q equals to 1, size equals to 3, probability equals to 0.5, and being the lower tail probability. That gives us the answer of 0.3125, which we can see is the summation of these two. Next, let's get the moment generating function of the negative binomial distribution. MGF negative binomial. This gives us the following formula. pe to the t divided by 1 minus 1 minus p times e to the t to the power of r. All of this to the power of r. You'll see that this is the same as the moment generating function for the geometric. So let's put that here. NGF geometric capital. Then we get, it's the same, but it's just to the power of r, the power of the number of successes that we require. So if we set that if the number of successes is equal to 1, then the negative binomial becomes geometric distribution. So nextly, let's look at this. What are the second moments? The second moment and the second centralized moment. So the expected value of x squared and the variance of x if x follows the negative binomial distribution, with the number of successes being 3 and the success probability being 0.5. And again, we'll make use of the NGF evaluator function and the order set to 2. So let's expand this so we can look at it. So the moment generating function for the negative binomial distribution is pe to the t over 1 minus 1 minus p times e to the t to the power of r, which we see is the same as the MGF if we just call negative binomial here. We get the formula for the second moment, which is quite a long-winded formula, but if you simplify it, you will find that it gives you second moment of the negative binomial distribution. And in this case, the value is 42. So if this function evaluated at t equals to 0 and p equals to 0.5, r equals to 3. The formula for the second centralized moment is the same as the variance, and we get the answer to be 6. That's the same as the variance of the negative binomial distribution, with number of successes being 3 and success probability being 1/2. So that's how you can use the MGF evaluator function on the negative binomial distribution to calculate its second moment. Next, we will take a look at the Poisson distribution. So if a random variable x follows the Poisson distribution and we let lambda be the number of arrivals per 10 minutes in a shop. So we have 5 arrivals in every 10 minutes of the shop. So let's take a look at that. What is the probability that the number of arrivals in 20 minutes is 15? So the first adjustment we're going to need to make is our rate parameter is 5 per 10 minutes. Well, now the time interval is 20 minutes, so we're going to have to multiply by 2. So it's 5 times 2. It's now 10 people arriving every 20 minutes is the new lambda, so to say. So with this framing of the Poisson distribution, we're asking ourselves, what is the probability that the number of arrivals in 20 minutes is 15? And we get that answer to be 0.0347, roughly. Next, for the cumulative distribution function, what's the probability that the number of people arriving in 10 minutes is less than or equal to 7? So this time we change it to q is 7 and lambda is 5 because we're in the same 10-minute interval. In the 10-minute interval, we have 5 arrivals in those 10 minutes. So the rate parameter lambda is 5. The quantile that we're interested in, q, is equal to 7, the number that we're interested in for the number of arrivals. So this gives us the probability that x is less than or equal to 7. And we see that that's around 86.67%. What is the probability that the number of people arriving in 10 minutes is greater than 10? Well, we're going to use the lower dot tail equals false, so we get the upper tail probability. We're in 10-minute interval, so we don't need to go adjust this lambda, which is 5 per 10 minutes. And q is 10. We're interested in the probability that x is greater than 10, where x follows the Poisson distribution with the rate parameter lambda equals to 5. If we submit this line of code, we'll get that answer, and we'll find that it is roughly 1.37%. Now, 0.0137 chance for us to have more than 10 people arriving in 10 minutes. How do we get the moment generating function of the Poisson distribution in R? Well, we just use the MGF function. MGF, and we call the distribution parameter to be equal to Poisson. So it's e to the lambda times e to the t minus 1. And lastly, let's look at the second order moments of the Poisson distribution. We know that for a Poisson distributed random variable, its expected value is equal to its variance, which are both equal to lambda. So we expect that this should produce the second centralized moment should be equal to 5, because that's the variance, which is equal to lambda. And indeed, if we look at this function, we see that it is the case. The second centralized moment, which is the same as the variance, is 5, which is equal to lambda. The value of the second moment is the expected value of x squared. And we'll remember from the shortcut formula for the variance is that the variance of x is equal to the expected value of x squared minus the square of the expected value of x. So we know that the variance of x should be 5, because that's what lambda is. The square of the expected value of x is 25. So we know 5 plus 25 is 30, which is this value of the second moment, which is the value of the expected value of x squared. Thank you very much for watching. I believe that this template will prove very useful to you to getting an understanding and an introduction of how you can use R for discrete distributions and all of the distributions that we have covered in the probability theory playlist. And I hope that you've enjoyed this video, and I hope that it's also given you a good showcase of the moment generating function package and how we can use it in R. Thank you very much for watching. Like and subscribe if you enjoyed the video. Boer Commander out.